So my name is Petr, and this is definitely not a sole work. Okay, this is better, yes. But a bunch of people were involved, as usual. And I will talk about the vulnerability in chips by Infineon that allowed us to attack their RSA keys. But I will try to make it more general, in a sense that I will describe how we get there, because it was not clear that we will just find this vulnerability, and also what we can do, also as a community, to prevent this in the future. Good. So how many of you are from Slovakia? Raise your hand, please. Great. So the first question is why we targeted Slovakians, so Slovaks' electronic IDs. And of course, the answer is we haven't. Because that was just a coincidence. In our laboratory, we spent a lot of time playing with the smart cards. We did that for our national security authority for a long time, then for open source world as well. And I really like smart cards. We are doing a lot of open source stuff for that. You are welcome to grab me after the talk, and I'm very happy to talk about that. Smart cards nowadays are everywhere. You likely do have maybe 2 or 3 smart cards which are programmable in your pocket. One is SIM card, right? Another is banking card. Maybe you do have authentication token. So this is really widespread technology. Yet, as is very common with the hardware industries, this is very closed industry. So forget about open source hardware here. Okay, there are some people pushing for that, but for the chips that are deployed en masse, then no open source really. And even just to get the detailed specification, you need to sign NDA, which I really don't like to do because then it prevents me to publish stuff and so on. It's intended for security usage, and this means it shall be secure, right? So if it's so closed, how we can verify that it's secure? And the answer is we can't directly, but we rely on certification laboratories that do this on our behalf. And there are basically 2 of them. One is from US, which is NIST FIPS standard, and a bunch of laboratories doing this certification, and the second one is Europe and the rest of the world common criteria. They do a nice job, but the problem is that the details of the certification evaluation are not that public either. So you can get a lot of information out of it, but real details, what exactly they tested and how it went and what were the techniques are not public either. So in 2014, what we decided to do was, okay, we have in our laboratory a lot of smart cards, and we know how to program them. So maybe we can program the smart cards to generate a large number of keys, and we started with the RSA. And by large number, I mean, let's make it 1 million. Some cards maybe will not survive, but let's get 1 million keys out of the smart card, and then take the open source libraries for which we do have the source code and generate the same number of keys and then try to find similarities. Maybe we can learn how it's implemented inside the chip, because everything is black box. So we decided to do so, and we started with RSA. How many of you know how the RSA works internally? The primes there, private, public. Okay, so just quick recap. You probably already know that RSA is a widely used algorithm for asymmetric crypto. You have 2 keys, and there are 2 main usages. First one is for digital signatures, and you are using this for email, SMIME, and stuff like that. Second one is for key exchange. So when you are connecting to HTTPS server, there is some handshake, and you are using the RSA or ECC during that period. So very prominent algorithm, I would say. And there are 2 parts of the key. One is public, one is private. Public is distributed to everyone. Private shall be secret. The private part or key generation phase works so that you will first generate 2 very large numbers. You will make these numbers to be primes, so you need to tweak them a little bit. And when you are done with that, you will just multiply them, and you are basically getting the public key out of it. Factorization attack is attack where you are given as an attacker just a public key. And that public key is really public, so you can just download it from some public server or try to establish a handshake with the server and get that out of certificate. And if you are able to compute the private key out of the public one, that's factorization attack. And that's something that definitely should not be possible. There is a small problem. These P and Q, these are large numbers, or large primes. And it's quite tricky to get such large numbers. Nowadays, we are using 2K RSA for the public key, which means these 2 primes shall be 1K each. And not every number is prime, right? So it takes roughly 500 plus minus attempts when you are just generating large numbers to get a prime, which is not really an issue on laptops, but it's a big problem on limited devices like smart cards. So people were researching clever ways how to at least speed up this a little bit, maybe 3 times, 5 times. It counts, because nowadays if you will generate a RSA keypair on smart card, it will take something between 2 to 200 seconds. And this is like slowing down usage. OK, so what we did. So we took, that time, 16 different smart cards, 22 different libraries, and just let them generate large number of keys. So we end up with a large database of keys, both public and private, and then we start to analyze them. The best analysis is always drawing pictures. So we start with stuff like we took most significant byte out of first prime, most significant byte out of second prime, and plot a dot into 2-dimensional graph. And because we have 1 million keys, we have 1 million dots, and then we can draw some heat maps, which is the case here. And then we did another analysis with a prime, and then we did an analysis with the public key, and so on. And we were surprised by the fact that these shall be just random RSA keys, whereas what we were seeing that time was that different cards, different libraries are producing slightly different keys. And we were investigating further, and we figure out that there are 7 implementation choices made by the developers of these libraries how to pick the prime. And these implementation choices, at the end, slightly bias the resulting primes. And because the primes are biased, and the public key is just a multiplication of these 2 primes, also the public key is biased. Okay, so we figure out, OK, there is very small bias. It's nothing about the weakening the security of the key. It's just small bias. So what we can do with that? We can take a certificate, extract the public key out of it, and then look at specific places for which we know that the bias is present. So we know that this particular bit is not half-time 1 and half-time 0, but it's slightly towards the 1s for this particular library, or slightly towards the 0 for another library. And because we do have already a database of a large number of keys, we do have a pre-computed matrix, which is there, which tell us exactly if you will see this particular biased bits, most likely it's OpenSSL. And if you will see other combinations, most likely it was some smart card. Okay, so that was approach we did. And you can get some kind of classification. Basically, someone will give you a public key, and you will get back the information how likely is that this public key is OpenSSL, Microsoft library, and so on. Okay. So is this vulnerability? Is it a big deal? So basically, think about that from now on, what you can do is, if someone will give you a public key, you will get some probabilistic information which library generated that public key. So what you can do with that? First of all, you can make some nice pictures again with the statistics like which library is most popular on the internet. What do you think? Which library is most popular? OpenSSL, for sure, right? OK, I need to change that. But yeah, definitely OpenSSL. But you probably don't need to use our fancy technique, because you can just see how many Apaches and engines are running around. But what is the exact fraction of the keys? Nobody really know before, because they were expected to be random keys. But now, with our technique, we can measure that. Another thing you can do is identify what particle organization is using as a library, and whether they use just a single one, or they have 5 of them, whereas it was expecting to be just a single one. So you can perform some kind of audit. And this has very nice usage that was published just this May. I will talk about that. If you will figure out that there are a large number of vulnerable keys on the internet, at some point, 0.5% of all keys on the internet were factorable. And the reason for that was that they were generated by devices that tried to create the keys when they just booted up, and there was no entropy at all, and they happened to have shared primes, and then you can quickly factorize them. Half of the percent of whole internet. It's really nice. And sometimes you can figure out that there is even a deeper vulnerability. So I will just quickly go through that. So this is a graph showing in time. So we are starting from 2010, where first scan of the whole IPv4 internet and corresponding TLS servers was made by Electronic Frontier Foundation that time. They made 2 scans. Then in 2012, people that were later showing that there are 0.5% of vulnerable keys made another scan, and from that time on, at some point it was once per week, and nowadays it's every day. So every day, someone just scanned the whole internet and save it. So we have a very nice data sets we can study. And using our technique, what we can do is we can then try to estimate what is the fraction of keys generated by OpenSSL, by Microsoft, and so on. Okay, so what you can see here, green is OpenSSL. So we are more and more dependent on OpenSSL. It's just going up. Blue one is Microsoft, which is more or less same, except for this dick down, where we were thinking, okay, how is that possible that previous day there was a lot of Microsofts, and the next day very few? What do you think? Okay, there was a problem in a scanning methodology of the company, and they figure out only a year and a half later. So then when they fixed, it was back again. And then you can see other libraries like Java libraries, the red one, and so on. So this is like nice statistics. If you will take a look on certificate transparency servers, who knows what the certificate transparency is? Okay, so this is Google's attempt to not be, what's the polite way? Okay, then they really don't have a good relationship with Symantec. So when they figure out that Symantec is issuing the certificates on Google's behalf, they decided to do something about that, and they set up the public server and said, okay, if Google Chrome is going to accept this particular certificate, it must be here, publicly here. Otherwise, we will just not let this connection to happen, or we will mark it as insecure. That way, they are forcing the Symantec to put their certificates there, and then, of course, they are checking from time to time. That certificate transparency, you can get a lot of information out of it, especially for open source intelligence. And there it's way more interesting. The whole internet has a lot of, it's not changing that frequently, but for transparency, you can see that every week different types of keys are there. You can also analyze what the company is doing, how they are generating the keys. So you can go to Amazon, generate, let's say, 10 keys using their interface, and then analyze these particle keys. And then you can use tooling that we provided. I have a bunch of links on the last slide. And based on that, you can figure out that Amazon is most likely using this particular group of libraries, very, very likely. Inside that group of libraries, it's not just a single one, but if you do have also private keys, you can rule some stuff out, and at the end you think that either it was Java or Bouncy Castle in a very new version that time, so it was Java. Another thing that came recently from Estonia was they are heavily using electronic IDs, way more than Slovaks do. And what they intentionally set up as a policy is that every citizen is assigned with a card, and keypair for that citizen is generated always on chip. It must be generated on the chip, so they can clearly say, we as a government don't have your private key. okay? Because it was generated only inside the key, inside your smart card. Then you know that these chips are built by some company, and keys generated by that smart card from that company will always have most significant byte from this particular brew range, okay? So it's not generating uniformly from 0 to 255. Instead of, it always has to be from this particular range. And most of the keys were, but they figure out that some keys do have most significant byte outside this range, which means they were not generated directly on that chip. And so then they started to figure out how it's possible, and then they figure out that Gemalto was injecting the keys from outside to speed up the process, they claim, but nobody really knows. And now the Estonia is suing the Gemalto because of that. So far, these were things happening, but when we were studying the different libraries and different chips, we were also seeing one particular library from Infineon when we were thinking like, okay, this is like strange. We were even joking like these strange keys and so on, but we were not really aware why this is so. They were like every time we perform some analysis, particle statistics, we got different results for different libraries, but this one was more different than others. So we were just seeing the difference more and more. It's always this library. But at some point, we perform very simple analysis. We took the public key and computed modulo small prime. So we computed the remainder modulo 3, modulo 5, modulo 7, and so on, up to 100, let's say. And because we have the 1 million keys, we got some distribution for these reminders. And for truly random keys, what you do expect is the picture on the left. Okay, so reminders shall be more or less equally probable. But for the Infineon, it was very different. And this time, that was like really telling sign, because if the public key has this particular algebraic structure, something has to be with the primes. So we were starting to search what is the structure of the primes. Random prime shall be just okay and random, whereas it turns out that the Infineon primes looks like this. Okay, so they are generated according to this formula. M, the big M, is a constant that we had to recover, but at the end we did. And then K and A are random numbers that were like generated truly randomly. The rest was computed. Okay, you may ask why they did that. I already told you. To speed up the likelihood that you will get the prime. Because numbers from this, with this format are more likely to be primes. Okay, but it turns out that because of this structure, we can factorize these keys. So we can take a public key and compute back the private ones. And sometimes academics claim something about the practical attack and so on, while the practical means 2 up to 80, which is not really that practical. It's like serious blow, but this one was really practical. So you can take your machine and compute things. We did that for half and 1K RSA, which is not possible to factorize if it's properly generated. And at some point, Estonians took public key of their head of electronic identity documents and factorized that one as well. And they claimed it took several thousand €. What is interesting, and at the end it helped with the mitigation, was that all these keys do have a specific fingerprint. Basically, you are searching for non-uniform distribution modulus, modulo, small primes. So you can very quickly find them, and you can then like discard them, revoke them, and so on. That was really helpful. We have a tool for that. We also built a tool for actual factorization, which was very helpful during the disclosure process, because then it was not just waving the hand, but we were able to send them the tool, and they run it on their side and said, yes, it works. Just to give you some idea, what is the speed up for the factorization? You can still, in theory, factorize 2K RSA, but it takes a huge amount of years. Nobody really knows, but like this is some guesstimate. While for Infineon, it was just 140, so way smaller. but these are still years. But what is the problem is this is perfectly parallelizable. So more cores you do have, faster you will compute. What were the impacted domains? Initially, we learned about that problem, and we knew only about one particular card we had. The problem with the smart cards is that most of the public keys of the people using these smart cards are not public. So, so we started to search various domains. We started to search TLS. Okay, around only 15 keys there were vulnerable. So we thought, okay, so that maybe it's not that big deal. These 15 keys were somewhat tied to SCADA system, so maybe someone made an extra effort to have a secure system. But we thought, okay, maybe it's not a big deal. Then we were also working on trusted platform modules. Who knows what the trusted platform module is? Okay, so it's basically smart cards tied to your motherboard, trying to help you with a trusted boot of your device. And because we already did separate research on this, we had some data sets, and then we figured out, okay, in our data set, 30% of TPMs are vulnerable. So then we also crawled GitHub. We got Yubikeys and extracted the keys out of them, and unfortunately they moved from one vendor to another one, and the second one was vulnerable. And then because our colleagues are also from Slovakia, they just took their IDs, and we figure out that Slovakia is vulnerable as well. Then we learned that Estonians do have the public repository of public keys, so we tried that one as well, and then it was like growing. So now the people estimate that roughly 1 to 2 billion of chips are vulnerable at the moment. What about the mitigation? Okay, when we notified the vendor, somehow it started to spread, the knowledge spread. It turns out that the knowledge is not spreading that well, because some countries like Estonia were probably not notified, or at least not notified so that they will realize what this is about. Slovakia was also not notified, or they claimed, okay, it's on the record. So, when you will learn that your public key is factorable, so what shall you do? So with the signatures, nowadays it's pretty easy. You will revoke the key, and because the signature is usually valid only if also the trusted timestamp is there, even if someone can factorize your key later on, he will not be able to forge this trusted timestamp, and so the signature shall be just fine. Bigger problem is with the encryption, because if someone gathered encrypted communication using these keys for Estonians, and they do use it really a lot, then okay, now they can decrypt everything. So maybe it's a good idea to build also the encryption system so that we can just revoke and then make the previous communication not decryptable. Perfect forward secrecy is the way to do so, but it's not always applicable. So lessons learned. First of all, it was not that easy for us to find a security contact with the Infineon. So at the end we were lucky, because via the academic channels we got direct contact to exactly right guy, because what we knew that time was that we definitely don't like to talk to lawyers first. So we first asked our lawyers at university, and they said, okay, do it, it will be fun. But like, that's the problem with the lawyers, right? But at the end, it was just fine. Infineon was very, very professional, and it was like kudos for them. The contact is important. So I tried whether Kiwi do have security contact, and I was surprised that like on 2 clicks I got it. So it was really nice. They do even lay out what you shall do. So they do have a public key and so on. So good. Only bad thing is if you will click on security TXT, it doesn't work. Sorry?
We are already fixing it.
Good. But otherwise, okay, this was way better than what we found for Infineon that time. Second lesson learned for me was secret design will prolong the exposure of vulnerabilities if there are any, and will make a lot of people stop searching for the vulnerability, especially if it's like very specific hardware, very hard to get, no documentation and so on. This also means that the vulnerability will be there likely for a longer time and therefore more damage. Okay, so there is definitely a trade-off, and I'm definitely in favor of more openness here. Nowadays, it's like common knowledge that we shall be prepared to patch everything, update everything, and so on. With a smart card, it's more difficult because a bunch of things is just burned into memory, which is write once, and you can't update it. Even parts that you can update, you need to do remote secure channel, or you need to ask people to come back to your police office or whatever. So this is creating a big bottleneck. Dissemination of the vulnerability. The problem here was we notified vendor, then the vendor is not directly selling to all end users. He's just selling to other big vendors, and these big vendors are then selling usually to states and so on. And you have something like that. You have 8 months of responsible disclosure, and you like to keep it secret while you need to notify a lot of people, so not that easy. And it turns out that it doesn't work really well for the Europe, at least. So what is the systematic defense against this? Because, okay, this is, I don't know whether it's a bug or intentional backdoor. I'm more in favor to think it's just a bug. But it doesn't really matter. We need to have systems that are able to cope with bugs like this. And one systematic defense is secure multi-party computation. Who knows what does it mean? Okay, good. So I will very briefly explain. So imagine that you have your secret program. Example is you trained with your private data neural network, and you like to let it run to classify the images. Also, the images that you will classify in future are sensitive, that's medical data, and you like to offload the heavy work to Amazon. Okay, but you don't trust Amazon, so you just like offload just the heavy work, but not give them your trained neural network, neither the images you will then process. And for a long time, this was not clear whether this is even possible. And in 2009, a guy from IBM, surprisingly, come up with a surprising, okay, that was ironic because IBM is like really invested, especially after they bought Red Hat, in cloud providing. So, so there is now technology for that. It's called homomorphic encryption. The promise is really great. It's slow at the moment, but it's improving. Okay, so it's definitely interesting to keep an eye on this. And if this will be fast enough, what you can do is you will come up with your program, run special compiler. This will output a binary. You can then run the binary on the Amazon, and Amazon will not learn neither about the content of the binary nor about the data processed. Okay, really great promise. Now slow, but it's getting better. Another point of view, you can take a look on these protocols, is that you have some really sensitive operation, like digital signature with private key. And you don't trust single entity because that chip can be vulnerable, backdoored, it may be just flawed. So you like to somehow distribute this sensitive operation among multiple parties. You probably know secret sharing protocols where 3 out of 5 people need to get to room, put their shares, and they will reconstruct the key, and then that key is used. This is a nice protocol, but the problem is that if the attacker can compromise that machine on which everyone put their shares, he will get or she will get the private key. So what we like to achieve is that all these separate parties will run something separately, never sharing something with the central party that is sensitive, and the computation on these separate parties will be put together in untrusted way, and result will be valid signature. Okay, so that's the goal, and for that we do have very nice protocols. So, and they are fast, efficient, and so on. It's not that generic as give me any program, I will compute this for you. It's specific like I will compute ECC signatures for you. Or I can run auction for energy where bidding and the bidders and these other guys will not learn anything except for the result and so on. But it can be tuned and then it's very efficient. So just to give you some examples from the smart card world, let's assume you do have a chip which is performing that operation and the chip is flawless. Or maybe it's not, and you will find that there is a bug. So what you will do instead, you will take a few chips, let's say 4, ideally from different countries, manufactured in different places, and you will set up the protocol so that even if 3 of them are vulnerable, random ordering, then the resulting signature and resulting private key will be still secure. Okay, so that's the goal. And with the multi-party, we can do so. By using a geopolitics here, you can like force, if they really need to get your private key, then US need to talk to Russia and China and European Union, and then they can screw you. So we designed a bunch of protocols, and we were not the first ones. We were interested in designing this, something that can run on actual smart cards. Of course, you don't need to have these parties to be all smart cards. You can have one smart card, one mobile phone, some laptop, some remote server. It's up to you. Okay, so the idea is to spread the critical operation. We're also interested in efficient implementation. So we started with just few smart cards. Then we bought way more of them, fit them into a device like this. You can fit about 60 smart cards there. But okay, then we thought, okay, we like to have at least 100. So we built a device where you can plug smart cards. There are 60 smart cards on one side, 60 on another one. And you can then run these multi-party protocols in parallel. So basically, you will take groups of 3 cards, and then they will run the multi-party protocol. And you can have a high-speed box doing the signatures, key generations, and so on. You may say that this is just some research 10 years before it will reach the market, but there are some stuff that is already here. Estonian banks or Baltic banks are using something called Smart ID, where they have just 2-party protocol, where one part of the signature is done on your mobile phone, second part is done on a server, which is operated by some consortium of non-for-profit organizations and banks and so on. And the idea is that you need, as an attacker, you need to compromise both of these parties. Otherwise, the resulting signature and private key is still secure. And what is really, really nice is that this is based on RSA. And the resulting signature will be just ordinary 4K RSA signature, which is really important for legacy systems because you don't like to force everyone to change their legacy systems. Okay, really nice. Another example, you will hear more about the U2F tokens. So I don't like to spoil too much how does it work. It's really nice technology. Yubikey, it's used as another factor to authenticate you against the GitHub, Google, whatever. And there is a challenge response, so you are getting some fresh nonces and you are signing them. So you have token which is able to do signatures. And you will have a different keypairs for different services. So different keypair for GitHub, different keypair for Google, and so on. And everything is nice, except for that the Yubikey 4 do have just one master key out of which they derive all these keys. And this master key is embedded during the manufacturing phase. Okay, so you need to trust Yubikey a lot with this respect. And people are not that happy about that. So what they did is they designed a secure multi-party protocol, surprisingly, that will basically solve this issue. And it's solved so that both token and browser will cooperate in initial generation of a master key, and then they will make it in a clever way so that the browser can always verify that the token is not lying and producing the proper keys that are not predictable. Also, another problem is that when you are authenticating with tokens, and you are using ECDSA, who knows what that means? Perfect. there is some padding, and a malicious token can use that padding to slowly leak your private key. So there is another multi-party protocol which is aiming exactly on that. Okay, and then build the device on existing hardware, so it's like backward compatible. You need to do some modification on the hardware as well, on the implementation running on that hardware, as well as on the browser side, but just the minor ones. It runs on existing hardware pretty fast, and no modification to relaying party is required. So this is really nice. And in a paper, it was published just 2 weeks ago, they said that it's already in use by company with tens of thousands of people, and 2 authors are working for Google. So I guess it's that one. So for take-homes and conclusions, certified doesn't mean secure, which was the case because these Infineon smart cards were really obtaining high security certifications. Don't trust black box design. If you are in a position that you can try to force suppliers to show you more about the devices, please do so. Single point of failure is a problem. You know that for many things, including people and hard drives and so on. Crypto shall not be another single point of failure, and we do have means for that, how to prevent this, multi-party protocols, many different flavors of that. So if you have any questions, I'm happy to take them. This is a bunch of links for what I talked about, because we are also interested in providing tooling that you can use and give us feedback back. So thank you very much.
Okay, so let's not use this. Sorry. Yeah, and I kind of messed up my schedule and wasn't able to prepare proper challenge worthy of such meetup. So instead of challenge in the end, we will have Yubikey for each speaker for the best question you will give. So speaker will choose whom of you will get a Yubikey.
With a master key inside.
With a master key generated by Yubikey inside, which cannot be regenerated.
Not yet.
Okay, so in case you have any questions, just shout, please, until we fix that mic.
I have TPM 1.2. How can I fetch it?
Okay, so if you do have a TPMs, which is mostly the case except for Macs, then if you are on a Windows, it's really easy. You will just open TPM MSC console, and they will tell you that it's vulnerable. Piece of our code is running inside the Microsoft detection service, and if it's not there, then you are fine. Also, what you are looking for is a chip with IFX as a shortcut, because these are made by Infineon, and these were all vulnerable. Yeah, check for that. Then what I was surprised was that the TPM can be updated. So they were able to create the firmware for that updated the vulnerable key generation. This one is part of BIOS update. So HP, Samsung, not Samsung, the other guys, they were making the updates for their particular boards. But like the initial update was made by the Infineon, and then they were embedding this into BIOS updates for their boards.
And if I have all motherboard and they don't make updates?
Then don't use Microsoft BitLocker, because Microsoft BitLocker do store the keys inside or wrapped by keys that are factorable. So then it's not a buy. Maybe you don't use the TPM at all. Okay, it's right now for Microsoft they use it for BitLocker, and maybe for some other stuff, I don't know. But the BitLocker was definitely the main usage at the moment.
I think one thing wasn't really certain.
So you are asking whether we can be sure based on one public key that that public key is vulnerable, right? Or okay, so then we can be really sure because you will just compute modulo small primes up to some high number, and you will, if you are always getting numbers that are fitting the infinite distribution, they are fine, and there is even a faster and more precise algorithm. So if you will be flagged, if you will run our tool and the tool will say it's vulnerable, you can be sure that it's.
But does it apply to only this vulnerable implementation or to all implementations?
No, it's just for this particular one. Okay, there might be different ones. We are trying to look because we really like smart cards. It was not like we hate them, but we just like to learn more how they are doing stuff.
Yeah, I have a dirty question about the primes. Because the more bigger you go, the more rare they are.
Yes.
And so when you tell computer that you have to give me 1024 bits or 2048 bits, they give you precisely the size of the prime, but someone can count like 1024 bits primes. I don't know, they can be 100 of them, and they can, for example, like multiply all of them by all of them, and basically do all the calculations, which will result in the like ultimate combination for the public keys, which are available.
The problem is that if you have the primes that do have something like 1,000 bits, there are not 100 of them. There are a huge number of them. So that's not possible. You can't compute all possible primes that way. So that's fortunately the defense.
Even when you are big fancy NSA or something.
For big fancy NSA, people speculate, and there is a paper showing how this is possible with the resources NSA do have, that they can do 1K. And there are speculation that they actually did that because based on Snowden documents, at some point they claim they are able to decrypt a large fraction of traffic. And so 1K is possible, but 1K, nobody should use 1K right now. We should migrate from 2K to 4K at least, or maybe elliptic curves, but okay, I'm not that happy with the elliptic curves.
That's theoretical.
Yeah, so it's plausible that NSA is able to do 1K.
Okay.
And I want to ask all the people from security that I know from Slovakia. The next day that it was published, there was a movement called eID.fail that promoted this kind of stuff. And there was a bug bounty program for 2,000 euros to hack the private key of the Minister of Interior. And then the government acknowledged that it's vulnerable. You have heard about that? Or
Could you please repeat the question, because I think...
Yes. Okay, so the question was about the eID.fail, or was it the name like that? Slovakia, when they tried to get the public key of the Ministry of Interior, right? And tried to factorize it, and they failed because it turns out he's not really having the public key anywhere, right? But okay, that's from my point of view, this was really a weak excuse that time. But basically, people contacted us whether we can do that factorization, and it was possible to do that factorization. It would cost several thousand euros, let's say, but at some point, because we do have a lot of guys from Slovakia, and they were not happy about the situation, they said, okay, we shall do this really. But there was no public key, so you can't factorize something if you don't have it.
Okay, one last question. You can probably choose
The last question will get the Yubikey.
Okay. How are you today?
thirsty because I'm not drinking before the talk, so I will get one right now. So thank you very much.
Okay, so let's not use this. Sorry. Yeah, and I kind of messed up my schedule and wasn't able to prepare proper challenge worthy of such meetup. So instead of challenge in the end, we will have Yubikey for each speaker for the best question you will give. So speaker will choose whom of you will get a Yubikey.
With a master key inside.
With a master key generated by Yubikey inside, which cannot be regenerated.
Not yet.
Okay, so in case you have any questions, just shout, please, until we fix that mic.
I have GDPR 1.2.
Two.
How can I fetch it?
Okay, so if you do have a TPMs, which is mostly the case except for Macs, then if you are on a Windows, it's really easy. You will just open TPM MSC console, and they will tell you that it's vulnerable. Piece of our code is running inside the Microsoft detection service, and if it's not there, then you are fine. Also, what you are looking for is a chip with IFX as a shortcut, because these are made by Infineon, and these were all vulnerable. Yeah, check for that. Then what I was surprised was that the TPM can be updated. So they were able to create the firmware for that updated the vulnerable key generation. This one is part of BIOS update. So HP, Samsung, not Samsung, the other guys, they were making the updates for their particular boards. But like the initial update was made by the Infineon, and then they were embedding this into BIOS updates for their boards.
If I have all motherboard and they don't make updates,
then don't use Microsoft BitLocker, because Microsoft BitLocker do store the keys inside or wrapped by keys that are factorable. So then it's not a buy. Maybe you don't use the TPM at all. Okay, it's right now for Microsoft they use it for BitLocker, and maybe for some other stuff, I don't know. But the BitLocker was definitely the main usage at the moment.
I think one thing wasn't really certain or clear from the lecture. Can you be sure which library created a certain key from just a single key, or do you need a large statistical sample?
So you're asking whether we can be sure based on one public key that public key is vulnerable, right? Or okay, so then we can be really sure because you will just compute modulo small primes up to some high number, and you will, if you are always getting numbers that are fitting the infinite distribution, they are fine, and there is even a faster and more precise algorithm. So if you will be flagged, if you will run our tool and the tool will say it's vulnerable, you can be sure that it's.
But does it apply to only this vulnerable implementation or to all implementations?
No, it's just for this particular one. Okay, there might be different ones. We are trying to look because we really like smart cards. It was not like we hate them, but we just like to learn more how they are doing stuff.
Yeah, I have a dirty question about the primes. Because the more bigger you go, the more rare they are.
Yes.
And so when you tell computer that you have to give me 1024 bits or 2048 bits, they give you precisely the size of the prime. someone can count like 1024 bits primes. I don't know, they can be 100 of them, and they can, for example, like multiply all of them by all of them, and basically do all the calculations, which will result in the like ultimate combination for the public keys, which are available.
The problem is that if you have the primes that do have something like 1000 bits, there are not 100 of them. There are a huge number of them. So that's not possible. You can't compute all possible primes that way. So that's fortunately the defense.
Even when you are big fancy NSA or something.
For big fancy NSA, people speculate, and there is a paper showing how this is possible with the resources NSA do have, that they can do 1K. And there are speculation that they actually did that, because based on Snowden documents, at some point they claim they are able to decrypt a large fraction of traffic, and so 1K is possible. But 1K, nobody should use 1K right now. We should migrate from 2K to 4K at least, or maybe elliptic curves. But okay, I'm not that happy with the elliptic curves.
That's theoretical.
Yeah. So it's plausible that NSA is able to do 1K.
Okay.
And I want to ask all the people from security that I know from Slovakia. The next day that it was published, there was a movement called eID.fail that promoted this kind of stuff, and there was a bug bounty program for 2,000 euros to hack the private key of the Minister of Interior, and then the government acknowledged that it's vulnerable. You have heard about that, or?
Could you please repeat the question, because I think...
Yes. Okay, so the question was about the eID.fail, or was it the name like that? Slovakia, when they tried to get the public key of the Ministry of Interior, right? And tried to factorize it, and they failed because it turns out he's not really having the public key anywhere, right? But okay, that's from my point of view, this was really a weak excuse that time. But basically, people contacted us whether we can do that factorization, and it was possible to do that factorization. It would cost several thousand euros, let's say, but at some point, because we do have a lot of guys from Slovakia, and they were not happy about the situation, they said, okay, we shall do this really. But there was no public key, so you can't factorize something if you don't have it.
Okay, one last question. You can probably choose
The last question will get the Yubikey.
Okay. How are you today?
Thirsty, because I'm not drinking before the talk, so I will get one right now. So thank you very much.